Tantor Audio, a division of Recorded Books, presents All These Worlds Are Yours, The Scientific Search for Alien Life, by Jon Willis, narrated by Eric Martin. Preface. All these worlds are yours, except Europa. Attempt no landing there. Use them together. Use them in peace. All these worlds are yours. The idea behind the title is that the search for life in the universe, both its practicalities and its implications, is accessible to anyone with an interest in science. The quote is taken from Arthur C. Clarke's 2010 Odyssey 2, and the use of a science fiction novel is deliberate. Many of our preconceptions regarding alien life have been formed within the imaginations of writers and filmmakers. Such acts of creative imagination are often quite stunning and profound, but perhaps in ways that reveal the nature of the human creator rather than some unknown alien. One result, however, is that we all have some idea of what forms alien life might take, whether they will greet us or just eat us, or perhaps greet us then eat us. Such ideas may well be anthropocentric, but when teaching the search for life in the universe to university students, I am always impressed by how eager the students are to move beyond popular imagination, and how excited they are to realize that science fact outstrips science fiction in coming up with new and radical ideas. Hence this book. 1. Alien Extravaganza. Do aliens exist? Is there life beyond planet Earth? Well, yes, there is. Probably lots of it. How can I be so sure? Sure enough to start the book by telling you the answer? My answer is in large part based on a mathematical argument. The universe, as we shall see, is a very large place, quite possibly infinite in size. We don't need to go into the math to understand that infinity means big. Big enough that, even though the possibility of something occurring, such as life, may be almost impossibly small, it must occur somewhere. The odds on your lucky lottery number may well be vanishingly small, but as long as the chance is not zero, if you play an infinite number of times, you are guaranteed to win. In an infinite universe, everything is possible. In many ways, though, this is an unsatisfying answer, one that locates alien life in the distant recesses of what we imagine the cosmos to be. Much more interesting are the questions: where is alien life to be found? What forms does it take? How does it live and breathe? And how should we interact with it? But, as we shall discover throughout this book, the answers to these questions are much more challenging to obtain than my rather facile yes in response to the question, do aliens exist? What happens if I change the question slightly? Is there any scientific evidence that life exists anywhere in the universe beyond Earth? The answer to this question at present is emphatically no. It is possible that this is because life does not exist anywhere in the universe except Earth. But, given my certainty expressed before, it is more likely that life indeed exists elsewhere in the universe, but we are yet to discover it. We haven't yet searched, scoped, poked, or peered into enough places in the universe to have found it. For full disclosure, I should note that it is also possible that we already have the scientific evidence of life beyond Earth, but that such evidence is not universally accepted as being proof positive. More later. Even once you have finished listening to this book, the answer to my second question will probably still be no. In large part, this is because the challenge is great compared to our current resources. Despite the claims of UFO enthusiasts, alien life has not spontaneously appeared on our doorstep. Alien life also appears to be beyond the current reach of our telescopes and space probes. In a world of limited scientific resources, we have to decide exactly where to search and how to search in order to achieve the best chance of success. Scientists refer to the ideas that underpin these efforts as astrobiology. The science of astrobiology has three main goals: to understand the conditions necessary for life on Earth, and possibly the conditions required by life in general, to look for locations in the universe which supply these conditions, and finally, to detect life in these locations. At present, we have discovered a great many potential habitats for life, planets and moons in our solar system or planets orbiting distant stars. Some of these new worlds replicate in part conditions we encounter on Earth, the only location in the universe where we know that life exists. At this point, the keen listener will protest as to why we use life on Earth as a template for the search for life in the universe. What if life on Earth represents only a tiny fraction of the range of properties displayed by life beyond Earth? Is our search too narrow in scope? Do we run the risk of missing truly alien life because we don't know how to recognize it? Once again, the answer is clearly yes. By starting with life on Earth and working outward, our search will not discover all possible life forms. We will overlook the consciousness of free-floating asteroid-like organisms and other unthought-of possibilities. But you have to start somewhere. The only life we know is that of Earth. By using this as a starting point, we can speculate about the kinds of life processes that might occur on planets similar to Earth, and by this I mean those that have a solid surface, an atmosphere of some kind, and possibly a range of chemicals in the liquid state. The only thing I can guarantee is that the more we look, the more we will learn about life and its possibilities. Okay, protest postponed? Let's proceed. We therefore stand on the threshold of asking whether life exists in specific locations in the universe, with all the attendant challenges of such an important yet basic question. What physical tests are required to unambiguously confirm the existence of what may well be an unfamiliar life form? What technology is required to perform such an investigation? Do we need to get physically up close and personal with the organisms in question, or can we learn about them remotely? Questions, questions, questions. The answers to which draw on a fascinating range of subjects: astronomy, physics, chemistry, biology, geology, mathematics, computer science, and philosophy, to name but a few. Although the range of concepts employed by astrobiologists is indeed broad, the ideas they represent remain very accessible. Though the ideas are certainly not what I would call simple, they do lie within the grasp of any scientifically literate person. So, with that in mind, the idea I want to start with is a very simple, yet very old one. It is the idea of a world. New worlds for old. A world is place. You can experience it, explore it, pick it up, and shake it. In some sense, it is the real world, as opposed to an abstract idea. For much of human history, Earth was the only such world. Hence we explored it, discovering new cultures and life forms. The stars and planets visible to the naked eye of classical astronomers represented a noble field of study, but the stars and planets they observed were ultimately considered points of light within a dark firmament. Myth and speculation attempted to describe their nature, but such ideas remained abstract, unobserved, and consequently imaginary. What changed was vision. We looked closer and saw more, and the more we saw, the more we realized that each planet and each star was a real place, governed by physical processes identical to those that had shaped Earth and our Sun. We could, therefore, encounter, investigate, and explore such worlds. We could visit them and stand on their surfaces. We could meet their inhabitants. Galileo Galilei was the first person to provide that vision. In 1609, Galileo tried to convince the merchants of Venice that his apparatus of two lenses attached to either end of a wooden tube was a good way to observe ships at a distance. While you and I would call the device a telescope, Galileo marketed the idea under the catchy name perspicillum. From his vantage point atop the bell tower of St. Mark's, he could observe ships approaching Venice up to a day's sailing from port. The magnification offered by his telescope allowed him to identify each approaching ship by observing its flags and pennants, information he offered to sell to their owners, who thus would have a day's head start on their competitors. It is not clear how much success he had in persuading the merchants of Venice to get a jump on the market, but at some point he decided to do something very different and very interesting. He pointed his telescope at objects in the night sky, among them the moon and the planets Jupiter and Saturn. Second, and critically for everyone thereafter, in 1610 he described what he saw in the simple, unadorned prose of the Sidereus Nuncius, or Starry Messenger. The moon turned out to be a world, a rather interesting one, with craters, jagged, unruly mountains, and deep, shadow-filled valleys. He suggested that the smooth, featureless plains were seas, Maria in the Latin of his text, the name we still use today. Importantly, all this was based on direct observation with his telescope. Until this point, the moon had been largely unknown, except for its regular motion about Earth. Classical astronomers had considered it a perfect, unblemished piece of creation, appropriately for an inhabitant of the celestial sphere. Instead, it turned out to be pockmarked, jagged, eroded, and resurfaced, much as Earth was, imperfect, complicated, and therefore interesting. From Galileo's first observations of the moon, it took us only 360 years to get around to visiting the place, poking, prodding, and, what will turn out to be of great importance for our exploration of the universe, bringing bits of it back to Earth. From our numerous manned and robotic explorations, we have learned that the moon is made of rocks very similar in composition to the outer crust of Earth. As far as we can tell, the oldest lunar rocks are the same age as the oldest rocks on Earth, about 4.4 billion years old, and slightly younger than the meteorites that appear to be the oldest chunks of debris in the solar system, about 4.54 billion years old. The inference based on these observations is that Earth and the moon were, at some early point in their history, one lump of molten rock. Some event, perhaps a collision with another planetoid in the young solar system, broke the Earth-Moon planet apart, the larger and smaller fragments becoming Earth and the Moon, respectively. In the 360 years bookended by Galileo Galilei and Neil Armstrong, the moon went from being a familiar yet poorly known voyager through the heavens to being a solid body with a long geological history ultimately twinned with that of Earth. Long before man stepped foot on the moon, it had entered our consciousness as a world, a physical part of our experience of nature, distant, yet real and tangible. The chances of anything coming from Mars are 1,000,000 to 1. So pronounces the astronomer Ogilvy in H.G. Wells's The War of the Worlds. Wells published the novel in 1896 for a public primed to consider Mars the next world in our growing collective consciousness of the universe beyond Earth. The man who more than any other prepared the public to believe in an alien civilization on Mars was Percival Lowell. His story is important for the search for life in the universe, although, as we shall see, his claims taught us that one should also bear in mind at which end of the telescope that life is. Percival Lowell eludes the simple sketch of biographical caricature. Though his ideas regarding life on Mars were ultimately flawed, he remained a serious scholar. Lowell could be labeled an amateur astronomer who formed part of a long tradition of independently wealthy men whose resources, coupled with their scientific drive, propelled many to become leading contributors to their field of interest. His decision to site Lowell Observatory, with its suite of telescopes, in the dark skies of Arizona, rather than close to the practical amenities of a large city, looked forward to the modern professional age, when telescopes are sited where their scientific observations can be most effective. Lowell's interest in astronomy was directed toward the planet Mars, a passion fired by the work of his peer Giovanni Schiaparelli. Schiaparelli, the director of the Milan Observatory, began his observations of Mars with the Great Opposition of 1877. In astronomy, opposition occurs when Earth and Mars, for example, line up on the same side of the Sun. The two bodies are often at their closest at this point, and thus opposition makes for good planetary viewing. When viewing Mars through a refracting telescope of the aperture used by Schiaparelli and Lowell, the planet appears as a pale pink disk, with dark blemishes apparent if the volcanic Tharsis Plateau is in view. Depending on the point in the Martian year in which one observes it, Mars will display the bright white of a polar ice cap that ebbs and flows as the seasons change. In addition, Mars experiences planet-wide dust storms that periodically obscure the entire surface, leaving what appears to be a featureless disk. Schiaparelli claimed that when observing Mars, he was able to resolve dark linear features on the surface, which he referred to as canali, channels. Schiaparelli noted that these features would resolve themselves in his telescope eyepiece only at brief moments of apparent atmospheric calm, when the blurred, restless image of Mars, agitated by waves of air pressure in Earth's atmosphere, stilled itself and revealed what appeared to be a clear view of the surface. So far, so scientific. Schiaparelli observed and reported what he saw faithfully. Though he speculated about the nature of these canali, he was balanced and cautious. But Schiaparelli's observations become the point from which Lowell could make a fateful leap of speculation. He claimed that Schiaparelli's canali were real features on the surface of Mars, and that they formed a global network. Such a network of linear structures would be unlikely to form via natural processes, and he instead claimed that they were evidence of a Martian civilization. Lowell expanded on Schiaparelli's work, producing detailed sketches of a Martian surface crisscrossed with a web of canals. It was troubling that other astronomers who attempted independent observations of Mars were unable to verify Lowell's claims. Lowell responded by questioning whether only the most powerful terrestrial telescopes, located at the best viewing sites, and by that he meant his own, would be able to resolve such features. As a leap of faith, Lowell's claims remain formidable even to this day. What reason would a Martian civilization have for indulging in a spate of spectacular planet-wide engineering? Consider that from Mars, even using present-day telescopes, one would be able to see few or no man-made structures on the surface of Earth, though if clever you would detect the glow of our cities at night. Lowell speculated that only some great need would drive the Martians to build on such a spectacular scale. Assuming that the red color of the Martian surface derived from a dry, dusty, dying planet, he dreamed that the Martian canals were aqueducts delivering life-giving water from the frozen poles to the center of Martian civilization on the equator. So far, so unscientific. Lowell had no evidence for these claims beyond the observation of fleeting linear features on the surface of Mars, glimpsed in what appeared to be brief moments of atmospheric calm. What changed? Telescopes changed. They increased in aperture and resolving power. The interplay of light and dark regions on the Martian surface and the blurring effects of Earth's atmosphere caused fleeting linear features. With larger telescopes and clearer views of the Martian surface, the canals faded like a dream upon waking, and thus Lowell's dream faded and died with him in 1916. But Lowell's passion for astronomy and the observatory that bears his name left a more permanent legacy. In 1930, Clyde Tombaugh, working as an astronomer at the observatory, used photographic exposures of the outer solar system to follow a faint smudge of light in orbit about the Sun. The smudge turned out to be Pluto, which at the time was, and for many still is, the 9th planet from the Sun. Billions and billions of planets? Do there exist worlds beyond the solar system? Looking skyward on any given night, your unaided eye will see roughly 3,000 stars in the night sky. There will be another 3,000 or so behind you on the other side of Earth. All these stars are located in the Milky Way galaxy, our galaxy. With the aid of a telescope, more, apparently fainter stars can be seen. Although it is not possible to count each star within the Milky Way, they crowd together to the point where they are difficult to resolve individually, we can count the total light they emit and compare that figure to how much light we expect a typical star to give off. Such light counting reveals some 400 billion stars within our galaxy. Each star is a sun very much like our own. Some are closer to us, some farther. Some are hotter and more luminous than our sun, others are cooler and fainter. Each is a luminous globe of ionized gas powered by a range of nuclear fusion reactions occurring in its core. In this sense, all stars belong to one family of objects. Our sun is accompanied by a system of planets. Do the other stars in the Milky Way host similar planetary systems? Many astronomers from classical times onward have expected to find planets orbiting other stars. There appears to be nothing special about our solar system, created from the dust and gas left over during the formation of the Sun. In addition, there is nothing special about our Sun. Many stars of similar mass and composition appear to exist throughout the Milky Way. Expectation does not equal discovery. It was only in 1995 that astronomers confirmed the existence of the first planet in orbit about a normal or main sequence star. The method they used was simple and elegant. Although the light from the planet itself is lost in the much brighter glare of its parent star, the planet exerts a rhythmic gravitational tug on its stellar parent. Rather like two eternally mismatched dancers, the smaller planet waltzes around its stellar partner, which in turn is drawn on a much smaller yet complementary orbit. The scientific term for this measurement technique is the stellar radial velocity method, more commonly known as the Doppler wobble. As seen from Earth, a distant star appears to approach and recede from us in response to its unseen planet. The planet discovered in 1995 is referred to as 51 Pegasi b. Its parent star is 51 Pegasi a, a sun-like star 50 light-years from Earth in the constellation Pegasus. The planet 51 Peg b orbits its parent star every 4.2 days and imparts a maximum Doppler velocity of 56 meters per second to its parent. For comparison, in our solar system, Jupiter imparts a Doppler velocity to the Sun of 12 meters per second as it orbits every 12 years. In a neat circle of logic, the same mathematics that Johannes Kepler, a contemporary of Galileo, used to describe the motion of planets in our solar system was applied to understand the 51 Peg planetary system. The results were surprising, to say the least. 51 Peg b turned out to belong to a new class of planet that we now call a hot Jupiter. The mass of 51 Peg b is likely half that of Jupiter, or slightly greater than half, but its short orbital period implies that it orbits its parent star at only 1/20th the distance between Earth and the Sun. Since 51 Peg a is a sun-like star, the surface of the planet, more likely a high-altitude atmospheric layer, is seared to temperatures of over 1,200 Kelvin. What is important for our story is that in 1995, we first discovered an extrasolar world. Although observed by its indirect effect, we know that 51 Peg A is accompanied by a planet, one unlike any we ever imagined. The Doppler technique reveals the mass of the unseen planet and the distance at which it orbits its parent star. Furthermore, our observations of the parent star tell us how hot the surface of the planet must be. To put it in perspective, we know almost as much regarding any given extrasolar planet as we did about the outer planets in our solar system before the beginning of space exploration. Each is a world. We can measure its physical properties. We can assess the extent to which each is a potential habitat for life. We are even at the very beginning of being able to search for the signatures of life in such extrasolar worlds. As of 2014, just over 1,800 planets have been discovered orbiting other stars. Some occur singly, some in multiple systems. This number represents those planetary systems that astronomers consider to be confirmed, usually via measurement of a stellar Doppler velocity signature. Some few thousand others, in particular those discovered by the Kepler space mission, which we will meet in Chapter 8, are considered candidate planets awaiting confirmation. Now, the careful listener will note that this section is titled Billions and Billions of Planets. How did I get from 1,800 to billions? Not all stars in the Milky Way have been surveyed for planets, but of those that have, a remarkably high fraction appear to host planets. Astronomers refer to this number as F-planet, the fraction of stars of a certain type that host planetary systems. It turns out that for normal or main sequence stars, which make up the bulk of stars in the Milky Way, F-planet is somewhere between 0.1 and 1, with 1 meaning that every such star hosts planets. Hang on a minute. That is astounding. Astronomers are used to dealing with numbers that are, astronomical, numbers so large that we don't have names for them. The mass of Sun, for example, is 2 times 10 kilograms. That's 2 followed by 30 zeros. The average density of matter and energy in the universe is 9 times 10 kilograms per cubic meter, which is 9 preceded by 26 zeros. In astronomer speak, a number between 0.1 and 1 is basically 1. So, within our order of magnitude approximation, a planet accompanies every star. If you were happy with my earlier statement that there is nothing remarkable about the makeup and contents of our solar system, then you should not be overwhelmed by this revelation. What is staggering is that as you look out on a starry night at those 3,000 naked-eye stars in the Milky Way, you should expect each one to host a planetary companion. Many perhaps have their own planetary systems. None will be an exact copy of our solar system. Yet, given the range of planetary masses and physical composition we expect to find, they are effectively identical. And when your imagination leaps to the 400 billion stars that we believe make up the Milky Way, you should expect to find 400 billion planets or so waiting there for you. It's life, Jim, but not as we know it. What will aliens look like? I think we all get the idea that aliens in movies normally look humanoid for 2 reasons. It is cheaper to portray them that way, and humans like to anthropomorphize aliens. There are many notable exceptions to this generalization, but the serious question is, what should our starting point be for recognizing alien life? While I am not ruling out that one day a Mars rover will capture a time-lapse image of a tiny Martian slug eking its way across a dusty plain, our search may well be subtler. The phenomenon we call life is a set of linked chemical processes, and the energy required by life generates a series of chemical byproducts. Breathe out and you will see what I mean. Therefore, our search for life would do well to consider how life processes alter the chemical makeup of a given environment. Chemical signatures resulting from biological activity are referred to as
Sample complete. Ready to continue?